Welcome to day 3.2, polynomial functions of higher degree. So what we're going to do is we're going to look at sketching some possible graphs of polynomials, all right? And we're going to start talking about the behavior, the end behavior, and the behavior at the zeros that we're going to talk about. So we're going to talk about even and odd powers of factors, x minus c, and this is the theorem that goes along with it. So if c is a real number, and x minus c to some power is a factor of that polynomial p, then the graph of the polynomial p of x will intersect but not cross. I call this bounce. So it'll bounce off the x-axis at the point c comma 0. And that's if the power, k, is even. Okay? It will cross or pass through the x-axis at that point c0 if k, the power, is odd. Okay, so let's look at this first example here of just graphing a possible, or sketching a possible graph of this polynomial. So what we're going to do is we're going to find the x-intercepts for the polynomial p of x. We're going to use the powers of those factors to determine the behavior at those intercepts. Then we'll sketch the graph. All right, we should be able to determine the end behavior and relative max and min values later on if we were to actually graph, well, the max and min values later on if we were to use our calculator. So if we're looking at this first polynomial, what we should notice is we're in factored form. So we should be able to identify our zeros or our x-intercepts by setting each of these three factors equal to 0. So we get three zeros, -1 from this guy, +1 from this guy, and 3 from this third x minus 3. Okay, so now we need to determine if it's going to cross or bounce at these intercepts, okay? Now, at x plus 1, at this x equals -1, okay, I look at my power. There's nothing there, so we can say it's a degree 1, so it's odd. So I know it's going to cross at the point -1 comma 0, okay? Same thing for this factor here. X minus 3 is being raised to the first power, which is odd. Therefore, it will cross at 3, 0. This middle factor, x minus 1 to the second power, 2 is even. So therefore, I know it's going to bounce at the point 1 comma 0. Now, we should state the degree, and we should talk about the leading coefficient. Now, how do I determine that the degree is 4? Well, I have a degree 1, and a degree 2, and a degree 1 again. If we were to add all those powers, we would get 4. So 1 plus 2 plus 1. So that's where we get the degree 4. It's a positive leading coefficient. There's a positive number in front of this guy, in front of this guy, and in front of this guy, and if we were to multiply those out, we would get a positive. So we know that far right and up and far left and up and behavior, okay? So now if we want to graph this, I kind of zoom in on my graph. I drew a little chart here, okay? I know at the point -1, 0, we're going to cross. I know at the point 1, 0, we're going to bounce. And I know at the point 3, 0, we're going to cross. So that's what the C, the B, and the C represents. I know my end behavior, they're going to end up both pointing up. Okay, so far left, I'm going to be up. I come back down. I cross at -1, 0. I have to come back up to the point 1, 0, but I know I'm going to bounce. So then I come back down. But eventually I have to cross again at 3, 0, and then I end going up. Okay, so what I want you to do right now is I want you to try the next example. Okay, now, a little hint, you have to factor example B. See if you can get at least the zeros, whether they cross or they bounce, identify your degree and your leading coefficient. Give it a try, come back and check your answers. Okay, hopefully you were able to, 1, factor completely, so you can pull out a -x, and then x squared minus 4x plus 4 factors as x minus 2 squared. So here's our factored polynomial. So we should have two zeros, x equals 0 and x equals 2. At x equals 0, my power is 1. So I know it's going to cross at 0, 0. When I set this guy equal to 0, we get 2. It's raised to an even degree, so I know we're going to bounce at the point 2, 0. I can go back to our original. It's a degree 3 polynomial, so it's odd, with a negative leading coefficient. So remember, we want to picture like a line with a negative slope. So I know the end behavior is going to look something like this, okay? Far left and up, far right and down. So now I want you to try graphing with this knowledge and see what you get. Okay, so taking a look at the right, we know we cross at the point 0, 0, and we bounce at the point 2, 0. I know I'm going to be far left and up. I come back, I cross, I go back up to bounce off of 2, 0, and I end up pointing down to the right. See if you can try example C. There are 4 terms you will have to group in order to factor completely. List all the zeros, decide whether they cross or bounce at those zeros, determine the degree and the leading coefficient. Come back and check your answers. So here's what I got. Factoring completely, I get x minus 4, x plus 1, x minus 1. So I have 3 zeros, all of which have odd degrees from their factors. So I'm going to cross at each one of those zeros. I have a degree 3 with a positive leading coefficient. So I'm thinking of a line with a positive slope for my end behavior. So it should look something like this. And you can see, so if I start far left and down, I cross at the point negative 1, 0. At some point I got to come back down and cross at 1, 0. And then again I have to come back up and cross at 4, 0, ending up, pointing up. Okay, our last example actually comes from the book, page 285, number 65. A company constructs boxes from rectangular pieces of cardboard that measure 10 inches by 15 inches. An open box is formed by cutting squares that measure x inches by x inches from each corner of the cardboard, folding up the sides. So if you take a look at this diagram, this will kind of help you. So we start with 10 inches on this side, but we cut out this square, and 15 inches on this side, cutting out this square all around. Okay, that is x by x. All right, so the first thing we need to do is we need to identify the volume. But what we want to look at is this diagram over here when we fold up the box. So imagine these squares are put away and we're going to fold along these dotted lines. So it's going to look something like this. So how did I get that this length is 15 minus 2x? Well, the whole length is 15, but I have to take away this x piece and this x piece. That's where we got 15 minus 2x. Similarly, the length of this side is started out with 10 inches, but I cut away x inches from both sides. So really this length of the box, when it's all folded, is 10 minus 2x. The height of this box right here is just that x number. So if we needed to express the volume, we have to remember that volume is equal to length times width times height. So that length is going to be the 15 minus 2x. The width is that 10 minus 2x, and the height is that x. So we should notice that this is a degree 3, degree 1, plus a degree 1, plus a degree 1. So we have a degree 3, the positive leading coefficient. So I'm going to take this negative 2x times a negative 2x, that's a positive, times the x. That's going to give me a positive leading coefficient. Okay? So we want to determine the x value that maximizes the volume. So really this is a calculator problem. So what we would do is we would plug this into our y1, okay? And we should get a graph that looks something like this. But what we're really focusing on is this part right here of our graph. So we can calculate that maximum, okay? And when you do that on your calculator, this is the value you should get. So what's the x value that's going to maximize the volume? I'm just looking at the x value there, so 1.96 inches, okay? We could even take it a step further and say, okay, why don't I care about this? Well, this is when the x value is getting too big, and we can only cut out so much of this 15 inches in length or this 10 inches in length. Otherwise, our box will be no longer. All right, so if you have questions on this, let me know, and we'll discuss it in class.